Hello, good morning. We are going to start in 1 minute. Good morning. In 30 seconds, we are going to start. Okay. Yeah, some seconds and we are going to start. Good morning. Okay, I think we are all in the webinar. So we are going to start. Hello, good morning, everyone. Welcome and thank you very much for coming to this webinar about new business opportunity from fusion to non-fusion applications, specifically for inspection and quality control field. First, notify that this webinar is being recorded, okay? So my name is Vanessa Ramos. I'm a technology transfer coordinator in Knowledge Innovation Market, the Spanish broker for Fusion for Energy Technology Transfer Program. With me from my team, it's Yaneitha Mendez and Mercé Cuixart. Good morning, Yaneitha and Mercé. Thank you for being here.
Good morning, thanks.
They are going to give us support during the webinar. On the other hand, we have the pleasure to have Carmen Casteras from Fusion for Energy. She is the IP and Technology Transfer Officer in this organization. So good morning, Carmen.
Good morning. Thank you, Vanessa.
Okay, so I'm going to pass the agenda. Okay. Yeah. So this is the agenda for the webinar. First, we are going to give a brief introduction about Fusion for Energy Technology Transfer Program. Then, Optic and Techniker is going to talk about three technologies, three potential developments to transfer in the framework of the topic of the webinar, inspection and quality control. After that, we will have time for questions. In this regard, please write your questions using the option that you have in the menu of the platform, of the Zoom platform, for question and answer. And please let us know who the question is for. And finally, we have the B2B meetings which have been scheduled previously. So in this regard, only people who have scheduled with us the meeting will be access to another virtual session to have these meetings. In any case, if someone wants to have a meeting or is interested in some technology, please let us know using the chat, and my team will manage with you the meeting, okay? So first, we start with the introduction section, and Carmen Casteras from Fusion for Energy is going to take the floor to introduce this organization. So Carmen, please. Thank you
Thank you,
for being
Vanessa.
here.
Yeah, so I work at Fusion for Energy as Intellectual Property Officer and Technology Transfer Officer. And what we are doing at Fusion for Energy is we are managing Europe's contribution to ITER. ITER, the ITER project, you may know, we are building the biggest fusion device in the world. Europe plus Japan, China, US, Korea, Russia, India. We are proving that fusion energy is feasible. But what is most important today is that we are doing this with the industry. What we are doing is we are placing contracts with the European laboratories and companies, and they are the ones that are manufacturing the components that we need. Size, complexity of ITER, you can imagine that we are not talking here of catalog products that we can just procure from the market. What we need are high-tech, non-existing, first-of-a-kind components. And this means that many times what we do is we develop from scratch, industry develops from scratch, goes and that extra mile in the manufacturing processes and generates breakthroughs for us. To give you a number, you can have a look at the budget. Europe is investing billions of euros in innovating and working with the industry. So we are an important source of new technologies. And we are also a source of potential innovation cases, business cases, because most of our technologies you will see can be applied in non-fusion applications and markets. So I can tell you, we are not just proving that fusion energy is feasible, but we want to increase the European innovation and competitiveness. And this is why we have a marketplace with technologies available for you that have commercial potential in non-fusion markets. And this is why we are here today to support companies to use our technologies. So Vanessa, I pass the floor to you. Go straight to the point and explain them how they can benefit from our technologies and from all this support that we are giving them. Thank you.
Okay, thank you, Carmen. So about the technology transfer program of Fusion for Energy, it is promoting the transfer of fusion technology to Europe's industries. This initiative, led by Fusion for Energy, is managed in collaboration with Inextenso Innovation Crescents, which has the role of prime coordinator. In addition, it works with a network of European technology brokers to identify industrial needs and successful technology transfer through projects and agreement. The brokers from this network are from Spain, French, Germany, Belgium, UK, and Italy. Our goal, as I have mentioned before, is to connect fusion and non-fusion ecosystem, looking for new markets and business opportunity for the fusion technologies, identifying their business potential and facilitating their commercial use. Our services are offered to all companies looking for new markets, opportunities, and it is important to say that all our services as a broker are free, so have no cost. Why integrating fusion technologies will add value? There are some reasons. One of the reasons is that fusion ecosystem is leading the development of breakthrough technologies in many areas, such as radiation, hard electronics, remote handling, magnets, control system, etc. On the other hand, one important reason is that these technologies have a high technology readiness level, which is a very important advantage. It means that no or few adaptation is required to fit with other applications. And there are many collaboration possibilities. For example, service agreement, licensing, collaboration through R&D project, etc. We invited you to visit our marketplace to discover the ITER-related innovation available for use. So you can see on the slide the link to see this technology portfolio. And we think that it could be very useful for you. If you are in industry, how to work with us? Okay, first you should contact our technology transfer brokers. You can contact the broker of your country in order to clarify your technical needs and your use case. After that, we can select, we can check which technology, which fusion technology could solve your problem, your needs, and to validate that, to validate the technical and economical feasibility of this match, this project, we will arrange a mediation meeting with the technical experts in order to study together if the technology can cover your problem. And as I have mentioned before, there are different brokers around Europe and in different countries. So in Italy, it's RINA, in France, in Extenso, here in Spain, Knowledge Innovation Market, and you can see on the slide my contact, RTC in UK, Berhard in Belgium, and Uran CESA in Germany. In this link, you can get the specific contact for your country or for the broker that you want to contact with. But on the other hand, if you are a technology provider and you have developed a technology in the framework of fusion for energy, so you have already worked with fusion for energy and you want to explore collaboration opportunities in new markets, the best option is to contact with Fusion for Energy IP officer, so with Carmen, or with in Extenso, the prime broker, in order to, firstly, be sure that your technology could be promoted with this program. So in order to validate your technology, that we can promote in the framework of technology program of Fusion for Energy. And if you can't, the second step is know how to do it. So we think that the better option is to contact with Fusion for Energy in this regard. And here you can see the contact for Fusion for Energy, as I have said before, Carmen Casteras, and for In Extenso Innovation Questions, Nicolas Liu is the contact person. Okay, so now we are going to give some examples about technologies available in our marketplace, specifically in inspection and quality control. And we have the pleasure to have Optic with Thomas Siegel, the head of R&D department, and we have the pleasure to have as well Techniker with Fernando Egaña, head of Mechanical Engineering Unit. So thank you very much, Thomas and Fernando, for participating in this webinar.
Thank you for inviting us.
Thank you. they are going to show, they are going to explain three technologies, three potential technologies. First one and second one are from Aseoptic, and the third technology is from Technique. So, Thomas, take the floor, and thank you very much for being here.
All right. Well, thank you very much, Vanessa, for inviting us to participate in this webinar, and a broader thank you to F4E for both the work that they've allowed us to undertake throughout the last 5 years that we've been working through and for them, and also with these added efforts for the technology transfer beyond the core developments that we've been undertaking for the ITER project. So first, I'll give a quick word of introduction to who we are at ASE Optics. We're an optical engineering firm, so we focus on custom developments of optical systems and metrology systems for a whole range of applications. One being major scientific installations, which, like Carmen mentioned, have some real requirements that cannot be met by catalog products. And this is where ASE Optics come in. So we work for ITER, for the IBBS, which I will present now, and the TAMS, which I will present afterwards, but also for synchrotrons, for one other kind lenses, and more broadly develop custom microscopes for applications beyond what's provided in the market. And more we're going towards more and more integrated systems that we can deliver as fully functioning. So I'll give a quick word of introduction to what the core of the 5 years that we've spent working with F4E has been. And it's a system called the in-vessel viewing system, which is part of the remote handling, but really is a diagnostic, which is designed for the detection and quantification of damage and erosion of the ITER plasma-facing components. As some of you might know, ITER is a big ball of plasma eventually, or will be a big ball of plasma eventually. And this plasma is likely to collide with the walls. And the kind of damage and the amount of damage that is being caused by plasma disruptive events or throughout erosion is a key factor for the safety of the plant. And therefore, the in-vessel viewing system is a system that can be deployed inside the vacuum vessel and enable the characterization and measurement of the ITER plasma-facing surfaces. So one of the key characteristics of the IBBS is that it can be deployed inside the vacuum vessel without breaking the vacuum nor switching off the electromagnets. So it has a set of characteristics which, beyond its metrology capacity, which is what I will detail in the kind of transferable, everything that is in there has been able to be adapted to these very extreme conditions, because it will have higher loads of radiation. You can see the IBBS in the lower right picture at the end of its deployment system. The deployment system was done by a partner company, Veolia Nuclear System. So it is pulled back during plasma operation, but it is deployed whilst there is still high levels of radiation from all the walls and all of the other components. Also, it can operate in 10 to the minus 8 millibar vacuum and in 8 Tesla magnetic field, which are very uncommon characteristics. Also, the kind of damage it is looking for are both small changes to see, let's say, defects in the plasma confinement mechanism, which might just show up by small changes in the surface quality of the plasma-facing components, and also quantitative evaluation of if there is proper damage or real erosion of how much material has gone, has it been redeposited somewhere else, and any volume defects which might have occurred. So the picture you're seeing at the top is the very first probe that we fabricated here at ASE. It's, I mean, on the ITER scale, it is very small. It's 140 millimeters cross section, and maybe a meter long, which compared to the size of a lot of other ITER components is little. And this is something that we at ASE, we have designed all of the probe, the optics, the scanning system, all of the data acquisition, and all of the electronics at the back as well as a software for data acquisition and reconstruction of the surfaces. So currently at ASE, we have this probe, and we have all of the system physically in our facilities. The way that the IVVS provides both, these first hints of changes and then the quantification of any real damage that has occurred, is to have two measurement channels. One which is called the viewing channel, which is really looking for changes in reflectivity of any of the plasma-facing surfaces. Because before material gets eroded or gets removed or replaced, or displaced, pardon, you start seeing some changes in the reflectivity. So the viewing channel is there to start detecting, before there's any volumetric changes in the kind of micron level or sub-micron level structure of the surfaces. And this is giving first hints to where you may get hot zones in the plasma, where you might get electron drifts or disruptive plasma events. And then you have a metrology channel, which enables a quantification of the volume changes to the plasma-facing components by any mishappenings in the chamber. And so together, they are able, throughout the ITER lifetime, to start giving the first hints and then quantify to see if there's any safety measure that needs to be implemented from the control system of ITER. So the way it works, what you can see on the end of the photo on the left is a prism scanner. And this prism scanner enables pretty much 4π steradian scanning direction to be implemented, which means the beam can basically be pointed in any direction around the probe through the use of two rotation stages, bar a 15-degree cone angle exactly back where the probe comes. And this limitation is compensated for by the deployment system, which you might have noticed before has an elbow in it, which enables to move the dark cone. So the scanning system rasters along some predetermined scan path along some of the plasma-facing components. This is a simulation of a potential blanket module where you can see 3 fiducials which are used for the alignment of the point cloud that's acquired with the CAD model. And then once the data is acquired, we transform the acquired data set from this kind of pseudo-spherical coordinates because of the prism refraction to an XYZ Cartesian coordinates. And this enables then a mapping and a differentiation of any features as compared to either a first scan in the case of having a reference scan originally, or compared to a CAD if no prior data set is. And so where you can see, for example, here there's a recess of 5 millimeters, and this is one of our very, very early scans. There's a recess of 5 millimeters that you can see in the middle, let's say middle left photo. And once one reconstructs the point cloud and matches the fiducials, you can see this recess showing up very clearly. And regarding the viewing channel, here what it measures is really the reflectivity of the instantaneous reflectivity of each point. And so for this one, either needs very accurate models of the reflectivity or or comparison to a previous scan, which is the mode of operation foreseen of the IVVS, is to be deployed before any plasma, take a reference measurement of the whole ITER vacuum vessel, and then perform the measurements periodically and look for differences in the reflectivity. So where beyond this very specific application of ITER, where can this be applied? So first I'll list some of the key specs of the system. Is one of its very impressive features is the accuracy and depth that it's able to reach over the length that it's able to reach it. So because of the limited deployment ports available in ITER, it needs to be able to measure, and then the sheer size of the machine, it needs to be able to measure all the way to about 10 meters from the probe. And even at 10 meters, it can reach accuracies of 6 microns. So this opens, if you're thinking of a 4-pi steradian sphere where a system can characterize with a micron accuracy over such a distance as 10 meters, this opens perspective for inspection of very small features in, let's say, very distant places from each other without specifically having to move the pieces within the field of view. The lateral resolution is limited by the focusing, and at the moment we're limited by the cross section, which has actually been reduced from the 140 millimeter that I mentioned originally, which was the spec we had for the first system, to 115 millimeters. And this leads to a lateral resolution just from the diffraction limit of the beam, the measurement beam, between 0.1 millimeter and 1 millimeter, depending on the distance, being able to reach smaller lateral resolutions closer by than further out. And one other limiting factor is the data rate compared to other inspection systems, which are operate in the megahertz. At the moment, the system can operate at 2 kilohertz, and it's foreseen they should be able to reach 5 to 10 kilohertz in the coming years. But it is kind of more or less fundamentally limited from the underlying technology to kilohertz to tens of kilohertz data acquisition points. But so when discussing with Carmen and other transfer people at F4E, we had some thoughts about where this could come in handy. So really, it's about, if you have something with a very tight tolerance that is spread over a large area. So for example, rivet inspection, where differences on the order of 0.1 millimeter can really affect flow of air around the surface. In fabrication lines, also, if you have a finished product which is not convenient to move, and you want to inspect several small features which are spatially separated, this enables to have a fixed system. And also high precision, let's say relatively large goods which are manufactured, such as turbines or other. Then I just wanted to show you a couple of example measurements that we've taken of just things that we had in the lab. So first of all, at the top, these are actual damage on ITER components, which have been heat treated to and beyond the expected heat fluxes. And you can see, to just give you an idea, these targets are 14 millimeters wide and 12 millimeters wide and 28 millimeters high. And the image that you see on the right has been taken at 4 meters. And so, for example, the little dimples that you can see in the middle targets, are millimeter to sub-millimeter, and even measured at 4 meters distance, you can really see them showing up, and they are quantifiable. Then we've taken two things that we had. One is a stool. The stool image has been taken at 2 meters from the sample, from the probe. And you can really see the details of the fabric, the creases, the screws underneath. So it's not an X-ray machine. We cannot see through. The image has been taken from a different point of view, where you can see by the shadow of the foot. But once you have your 3D cloud of points, you can rotate it in a direction that you want. And also we've taken an image of a €1 coin. This is again through the metrology channel. So the color coding that you see is a depth measurement. This measurement was taken at 4 meters. And this can really give you a feel for the kind of features that can be brought out by this kind of system. So this is it for the IVVS itself. It's a very, very interesting and very promising technology, and it has demonstrated a few things for us, which are one was the ability to perform the measurements with the accuracy that ITER required, which, down to kind of, their requirement was on sub 100 micron accuracy on 10 meters. And this has been able to demonstrate further. But also the adaptability of all of the components to the ITER environmental conditions. So obviously, if we were going to transfer this to an application, a lot of these requirements would be relaxed, because there's only very few places, namely the sun, where all of the and ITER, where all of these requirements are together. But this demonstrates our capacity at ASC to adapt any system to the environmental requirements and the technical requirements that might need to be undertaken. And this leads me to the reflectivity measurement system, which, let's say, is the IVVS's little sidekick, which came up in the last couple of years. And this came about because one of the big questions of the IVVS and its ability to measure is not only on precision and range, but also, I don't know if you have seen pictures of the foreseen ITER vacuum vessel, but the components are very shiny. And one thing that is known in metrology is it's hard to characterize surfaces which are very inclined from the field of view, especially if they're relatively polished, because there is just very, very low backscatter. When you're essentially looking at a mirror, you don't see the mirror, you see what's being reflected from it. And this measurement system, the IVVS, is essentially designed to measure something that is quite mirror-like at the start of operation. But what has been shown in previous tokamaks is that the erosion from the plasma does kind of soften the surfaces. So one of the big questions is how much light are we actually going to get back when the IVVS is going to get deployed in the vessel. And so to do this, we've developed this system to measure reflectivity. So there are a lot of systems out there which are able to measure reflectivity, but typically you take your component, you put it in a machine, and then the machine rotates around it. And the issue with the ITER components is they go through a lot of surface processing through the manufacturing process. So once they are assembled, and this will lead to Fernando's talk, you will see components that are meters in size and weigh tons, and therefore you cannot take bits and characterize them. So this system has been developed to measure the back reflectivity of components that are too big or too toxic, because there is a lot of beryllium being manufactured for the first walls as well. And therefore, it is a reflectivity measurement system which can be deployed over or around a component And what it does is point at a particular point. You can see here the demonstration, and this robot arm enables the probe to be rotated around a fixed point, which the system determines, whose position the system determines. So this system, to be compatible with the ITER requirements, has been developed to have very high dynamic range and work at the 2 wavelengths which the IVVS operates, with 1550, which is where the metrology happens, and 800 nanometer, which is where the viewing channel happens. We have some requirements on time. So when we do deploy the TARMs in factory where the components are being fabricated, or in other tokamaks, we're able to get significant data sets in the time that we are able to be allocated. And then we can feed this data into the models of ITER, which have been developed by F4E, and therefore be able to have quantitative estimates of the coverage of the IVVS. So the initial measurements that we've done so far show that the IVVS can meet the requirements of 95% coverage and even beyond. Some of it is just purely geometrical. There's some components one can't see, but 95% of the plasma-facing surfaces are within the range of measure of the IVVS. And so here, what does this enable beyond ITER? I mean, one of the hot topics at the moment is LiDAR is going everywhere, and one of the questions of LiDAR is, what can it detect or not? And this again is based on how much light will get reflected from the various objects that are within its line of sight. And this is one application that came up in a conversation a few days ago. But typically, anything whose backscattered reflectivity needs characterization for whatever application in a component that is too big to be moved or too toxic to be moved is where the TARMs can be applied. So on this, I want to thank you very much for your attention, and I will hand over to Fernando.
Thank you very much, Thomas. Very interesting. No doubt about the possibilities of these technologies. So thank you very much for your participation. We are going to pass, sorry?
Thank you.
Okay. We are going to pass to Fernando, to Technique. So Fernando, thank you very much for coming. And I'm going to give you the control. Okay, 1 second. Okay, so go ahead. Thank you, Fernando.
Okay, oh, sorry.
Sorry.
Thank you for the invitation to this webinar and give us the opportunity to explain what we have developed for Fusion for Energy to verify some specific parts of ITER components. The idea is, okay. The English of my presentation is a brief description of my company. What is the purpose of the requirements of the client and the project specifications? A description of the product, that is the multi-link inspection tool, is the name that this product has, and it was given by Fusion for Energy because it was a specific requirement from the metrology group of Fusion for Energy. Some results and a summary of the presentation. Okay, we are a company, a non-private foundation. We are dealing with research and development and helping the companies. We are located on the north of Spain. We have near 40 years of experience in working with clients and with different research institutions. And we are specialized on manufacturing. We have last year near 25 million euro of total revenue, and we are near 300 persons. We are in a stable situation. We have more main four areas of activity: advanced manufacturing, product engineering, surface engineering, and information and communication technologies. And for the case of this of the product that I will present, let's say that we have combined two of our main technological solutions. One is the development of special and unique, normally unique prototypes of mechatronic systems, and also our capabilities in inspection and measurement. With these technologies, we were requested by Fusion to analyze or to provide a metrological tool to verify a specific part of the cassette body, the multi-link hinge. In the lower part of the slide, you can see that obviously ITER is very big facility, very big installation. Is made by parts, but those parts are not small, and they are manufactured alone. But you have to assemble there, and there are a lot of problems to verify if the parts are manufactured correctly. In this case, we are not talking about a tool to make inspection of the global installation. We are talking about a tool developed for the acceptance of the validation of big parts, as is the case of the cassette body. In this case, Fusion was obliged to provide a procedure, a tool, or something to assess the geometrical tolerances of the virtual cassette body. In this case, the multi-link hinge. This is the part where probably it's better see on this slide. As I say, for assembly, there are this hinge that has to be done with a very strict tolerance. So if you request that tolerance, you have to provide a method to assess that you are fulfilling those requirements. So this is why, and this procedure should be traceable and should be easy to done and should be referenced to all the assembly. So it's not helpful or it's not valid to use a calibrated bar, for example. So something that is portable, as Thomas said, is needed to go to the part and not to take the part through a CME machine, because it's not feasible. So the metrological tool has to be sent to the manufacturing facilities and on site be able to measure the aspects that are on that table: the hole diameter, the roundness, the envelope, and the point coordinate. So for that, with a very low in uncertainty. Here, I want to talk about the tool you have developed. At the end is a portable CMM that consists on a measurement head based on confocal sensors. We have 3 lines of confocal sensors that go inside the hinge and obtain the distance from the head to the hinge. So with that, with 3 lines of measurements, we can reconstruct the cylinder that we have and obtain the required measurements. This travel has to move along the hinge with a total travel near 300 millimeters. And we have also very strict requirements of weight, because it's something that has to be done by hand. During the development, we found some problems with the confocal technology. It was not able to provide a good measurements without noise. So we have changed the concept from pure optical system to a mechanical probing system. As it's shown here, we introduce on a compliant mechanism a sapphire ball that is always touching the mechanical part, and we measure the center of that sphere. With that, we are sure that we are measuring correctly. What we have done in this case, we have started from the requirements. We were in a very good collaboration with the Fusion for Energy team, defining from the design if we were complying with the requirements. So we start from the functions, we analyze the operation conditions, and we develop a design. We make different kind of analytics, or also numerical analysis, and make a design that was accepted by Fusion. After that, we complete all the manufacturing, assembly, and tests. And after that, we pass a specific validation and acceptance test at Techniker in presence of Fusion of Energy. So, as another special need is that an alignment procedure is needed. So we have developed also something very interesting, that is the alignment procedure, using first a system with cameras that identify if because we are measuring a 45 millimeters hole with very strict tolerance, so we need to assure that there is no collisions when we are introducing our measurement head inside the hole. So with this pre-alignment procedure, we can assure that the system is well aligned with the hole that it has to be measured. On the right side, you can see how this system is calibrating with against previously well measured cylinder, and this is the previous test that you have to perform before going to make a measurement. Even if it's a first prototype, at the end it's a product, it's a unique product, and we have also to provide all the components, transportation system, control box in a easy to transport system, because as I say, here in this case, the measurement element has to go where the part to be measured is. Here is a summary of what the MET is able to do. We have created easy to use user interface where the user, after the MET is located, in this case, is fully inserted in the hole to be measured. So on the screen during the measurement, the three confocal sensors are giving the measurements. At the same time, there is an estimation of the diameter that is measurement. It's only question to check. And the position also where it's measuring is also given. All this process is automatic, and a complete file is generated. This file that after doing the measurement is processed and give the results. The results on the screen is only to check during the measurement that the user is doing the things right. But it was requested from Fusion that the raw data was also given to them in order to provide it, to analyze themselves the results. Summary. I think this is, in this case, this tool is a dedicated tool for fusion for energy requirements. It is able to measure internal long holes with a length of, in this case, for 350 millimeters, and for especially provided for 45 millimeter diameter, with an automated measuring procedure and alignment procedure. It's a complex mechatronic device. Which are possible applications? In this case, I think that the tool itself, as it is, it should be updated to measure other kind of internal holes. But its main advantage is that it combines optical and mechanical touch probe technology, avoiding problems that normal confocal sensors could have when you need very accurate measurements in reflecting surfaces. It's able to do log hole measurements. It's scalable on size for other diameters. Here, everything was requested to be very compact inside the box. So it's difficult to change the measurement head, but it's easy to replicate it for other kind of diameters. And also, if the tolerances are relaxed, the uncertainty tolerances that we were talking about, 20 microns, it could be, for example, design different measurements that could be interchangeable. And also with other configurations, it's a tool that could be useful for characterized planar surfaces. And I think that in a very fast way, I think this is the main, let's say, characteristics of the tool you have developed. I have to remark that this dedicated tool is portable, very accurate, and its main characteristic is that it's able to measure internal holes to obtain different characteristics of those holes.
Okay, thank you very much, Fernando. I think that it is a very promising technology as well. Thank you, Thomas and Fernando, because both of you have met the time perfectly. So thank you very much for that.
Thank you.
Okay, so we are going to pass to question and answer session. And please, if you have any question, let us know through the application. I think that my colleague Janeitha or Mercé is managing the questions. So Janeitha or Mercé, are there questions?
Hello?
Yeah.
Yeah, we have two questions for Thomas. Okay. The first one is from Philip Rowling. And the question is it a real-time inspection process or a three-step inspection process? Raster acquisition, 3D data computation, and then human analysis on data?
Okay, so currently, at the current stage of the development, is a very sequential process. But especially for the kind of data rates that we are talking about, which is like 2 to 10 kilohertz, it would not be a wild process to be able to make it a live inspection tool. But the current implementation is a step-by-step process. This is mostly software development, and that would enable this. But it would have the capacity to do it.
Okay, and the second one, also from Philip to Thomas, is technology dependent to analyze its surface features, reflectometry, etc.?
I am not sure I understood the question, but I think so. Is this related to the TOMS or to the IVVS?
I think it's the second one.
Yeah. So the reflectivity measurements can be performed on pretty much anything, any shape, and any material. We have 100 decibels of dynamic range, so it really allows us to inspect very, very shiny surfaces up to very large incidence angles. Anything that has a more diffuse style of reflectivity will be easier.
Okay, I think that the same question could apply for the first technique
Yeah.
that you presented. So maybe you can say something.
But yeah, so the dynamic range of the measurement. I mean, you saw in Fernando's presentation examples of the diverter targets, and you can see they're definitely very shiny. So the dynamic range of the viewing channel has been characterized and reaches about 100 dB. The metrology channel, just from the inner workings, it's a little bit harder to characterize and get a numerical value. But definitely we have acquired data at 80 degrees incidence on samples. They're not quite mirrors, but they're very much in the likes of the one that Fernando showed.
Okay. From Dominic, we have another question to Thomas also. Wait a second, Thomas. Oh, okay. Is it surface inspections or also in-depth thickness inspection?
So that particular system measures distance. So it's a single surface measurement, and it can all see through. So for thickness measurements, we also have, which was part of the development, not for F4E technologies, also based on interferometry that enable multi-surface measurements in a single shot. Something more in the style of optical coherence tomography, just on a slightly larger scale. But this only for, let's say, transparent and turbid media in something that would be made out of metal, and we would only be able to inspect the visible front surface. Okay,
thank you. Francesco Becchi, this question is for Fernando, I think. If I correctly understood, the technical tool is a contact tool. I cannot understand how the fingers are deployed on the component. Is there any preset for a given diameter? The test, sorry, wait a second. And the test, okay. The test mockup on the picture is a solid block, while if I am correct, cassette hinge has several discontinuities.
Yes, we have to.
So the question I think is there any presets for a given diameter?
On this case, the preset is calculated. The flexure is calculated for the tolerances of the cast hinge, because yes, it's not continuous, is discontinuous, but we have to do it with the acceptance of fusion for energy.
Okay.
It's not valid for any diameter. It's only valid in this case, the preset of the measurement head for the tolerances that are accepted for the hinge.
Okay.
And it's a previous check has to be done, inserting a bar to assure that the diameter is complying with the first tolerances before to make the measurements, in order to assess that you are not damaging the measurement tool.
Okay. these tools just could be applied for holes measures, or you can use it on other geometries?
At this moment, you have 3 scanning lines. So if you are, for example, against a planar surface, you only have the possibility to orient one scanning line to the surface. But the technology could be updated or scaled to other kind of measurements with other kind of measurement head. But at this case, it's a cylinder with 3 scanning lines. So it's dedicated to holes in principle.
Okay, and this question is for both. What is it necessary to adapt this technology to another sectors? What is the first step that the industry have to do?
So I think conceptually is looking at what the requirements, the final requirements are, because the ITER ones are very specific to the ITER problematic, at least for my one. I'll let Fernando talk on their side. But is to define what the requirements are. We can currently do demonstration measurements. If someone wanted to send us a sample, we would be able to just measure it, and you can see with the applicable current requirements what the machine is able to do. And also in terms of environment, because a lot of the cost drivers of the instrument are because of magnetic radiation and other compatibilities, which are very unique to ITER. So for us, the first step for anyone interested in applications beyond fusion would be to contact us with the requirements, and would be able to adapt the design to this.
On our case, is the same. I think that the first step on a development is to check the client requirements, and in our case, as the inspection is not done on ITER facilities, the radiation restrictions that are present in the case of assay optics are not present. But yes, very strict tolerance of uncertainty. So that is the main cost driving in our solution. If the uncertainty, for example, is a little bit relaxed, the development could be cheaper, or for example, could be not needed the touching probe, only optical measurement device could be present. So the first step obviously is to check which are the requirements. Contact us, and we will kind to try to update the development to the requirements.
Yeah, if I may, Janessa.
Okay.
What has a lot of value is the know-how that both companies have gained to feed the requirements. So it's not here offering a very specific tool, but the possibility to build a tool that can do what is required in ITER, so it can do it can be useful for a lot of other applications. Not the tool itself, but the possibility to build it.
Yes, I think in our case there are a lot of combination of technologies. One is the confocal technology to measure, but also we have assured that we are going inside a hole with without errors, maintaining our measurement tool very aligned with the process. We have an alignment process with cameras. We have also included fiducial points to reference our measurement to the global system of coordinates, and all of those things are integrated with easy user interface, processing tools to in an easy way process the results and obtain the data that are requested by clients. I think with clear requirements, things that are used on this development could be updated for other demands.
Okay. What kind of no fusion application have you already identified?
I think in our case, it's not a fusion application, it's a manufacturing application. We are checking that something that is machined is complying with the requirements. In case that you have very strict tolerance in a very big machined part, and not only in a local place. You have different features. For example, each diverter has, I think, 4 or 6 different hinges that you have to inspect one by one and relate one to the other to a external system of coordinates. So any kind of machined part you have to verify is susceptible or use this technology. In this case is not strictly fusion for application. Is any big part that has to be verified by or with very strict tolerances.
Okay, and Thomas?
And yeah, and from our side, it's mostly similar applications of fusion as Fernando mentioned. It's large parts with very tight tolerances.
Mm-hmm.
So we would not be able to measure shafts at all. That would be a very specific geometry that that our technology would not reach anywhere near the MIT tool. But anything that has large dimensions and tight tolerances on kind of micron level, let's say meter scale components that have micron level features and which need to be toleranced is where we see the key applications of the IVVS.
Okay, thank you very much. We have a question for Carmen and Vanessa, and is what opportunities and challenges could be anticipated in transferring fusion technologies, which were developed for first of a kind of component and extreme condition to mature industries?
I don't know if you want to.
It will depend, I believe, Vanessa. It will depend on the technology to be transferred.
Yeah, and maybe
what we are experiencing is that it has to be customized, but it's not. The challenge is not different from applying a technology that comes from another company to another one.
Yeah, maybe there is some technical barriers and depends of the technology, of course. But maybe we can say to the audience what kind of collaboration they can establish in order to transfer these kind of technologies. Okay.
Normally, what we are is the companies that have developed the technologies, the ones that have the know-how to do it, and normally it's service contracts.
Okay.
And when a very specific design or a manufacturing process is needed, it could be a license agreement. But most of the times we are talking here of know-how and skills that the best way to get transferred is through a service contract between companies. So it's the most effective way.
Yeah, because
it's knowledge transfer.
Yeah, exactly. A lot of knowledge on the background.
And when, if for instance, if we are talking of a software, then of course we need to grant them the rights to use the software, right? But
right.
This is just to allow them not to infringe our intellectual property. But this, for me, this is secondary. For me, it's most important. There is a business case. And there is a benefit from both parties, and then we grant the license agreement. So from a legal IP point of view, all is very clear.
Okay, thank you, Carmen.
Okay. Janaisa?
We don't have more questions. So.
Okay. So thank you very much for your question and for answer for these questions. So before wrapping up, just to say two things. First, that we, the Fusion for Energy Broker Network, are organizing 3 additional webinars focused in other topics, advanced manufacturing, simulation and modeling, and remote handling for January and February. So please stay tuned to our social networks and communications. And on the other hand, other important things is that it's about the funding opportunities for Fusion for Energy, from Fusion for Energy Technology program for the next year. So again, please pay attention, stay tuned to our social networks, and that is all. We hope you enjoyed this webinar. Thank you very much for your attention, and thank you, Carmen, thank you, Thomas and Fernando. So that's all. We are going to pass to the B2B meeting, which the organization which are said before. So please, for this organization, use the other link that we have sent you, and we will see you in 1 minute. Thank you very much.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Bye.
Bye.